Hello everybody, hello, how are you? Today we will be making a chapter review about calculus, and the first episode will be on limits, differentiation, differentiability and continuity, and also first principles of differentiation. And today we have Ege. How are you, Ege?
Hello guys.
We took some notes and we try to make them as colorful as possible, as fun as possible, and then we also share them on felsefesinde.wixsite.com/home. You can grab your Felsefesinde card directly and reach out all the notes that we are sharing about IBDP and also some other private content that we are producing, especially for Felsefesinde card users, and it's completely free, and we believe that it will really help your IB journey. So shall we begin again?
Let's begin.
Okay, so today's topic is about limits. I will start with limits, and I drew a graph here to directly show you what limits work, how the limits work. So first things first, we have a graph like this, and we can see that at x1 the y1 value is not fulfilled, but y2 is filled, so it doesn't have that part. And we have three important things about limits. The first thing is that the notation is just like this, limit, and we show x goes from where to where. So we can see that x is going x1, and you may see this negative and plus signs at their top. The negative sign means that we will approach the graph from the left side, from negative infinity. Just think like this, okay? We will approach from left. I used also color coding. You can see that the pink one is going from left. It's negative. So as I follow it from the negative, the orange line, I come, and I approach x1, and I realize that I will end up reaching y1, not y2, because I came from left. However, if you check the green color code, you will see that the x is approaching to with an arrow x1 plus. Plus means that from the positive side, from right side we are approaching. And I came down the orange line from the orange line, and I try to approach x1 to my limit, and I see that the limit is y2, not y1. So I hope this part is clear. Anything you want to add again to what we said here? Very good. So let me show you an example. How do we use them in real functions? So let's say we have a function fx, and this is equal to 1 over x minus 4. Let's find the limits for points at 4. So we can see that I firstly approach from the left side. Okay, I said negative, and you can see the color code pink again. So I will add 4 minus. We just substitute the number that is below our limit notation into our fx function. So 1 over 4 minus, I will tell you why I am still keeping that minus sign over here. So 1 over 4 minus 4, this makes 1 over 0 minus. What does that mean? Obviously, this result will give us negative infinity. I kept this minus especially to show you that we are still thinking about the left side. I came from the left side. And the second limit that I'm going to check is 4 plus, meaning that I will approach from the right and try to reach x is equal to 4. So I substitute 4 once again for this notation, and I keep the plus sign to understand and remember whether if it will go to positivity or negativity. So 1 over 4 minus 4 once again, and it will be 1 over 0. This is infinity. 1 over 0 means infinity. However, we will see that this has a plus sign, so this is plus infinity. This goes to plus infinity. So let's see if we were correct or not. Now, and yes, we were right. Why? This was the function that we mentioned, and 1 over x minus 4. So I said up here that I approached from left, 4 minus, x goes to 4 minus, and the pink line goes in that direction, goes from left and tries to approach the 4, and we found negative infinity because x is equal to 4 is a vertical asymptote. It will always get closer to x is equal to 4 but never approach it. So it approaches that point at infinity, however negative infinity. And we can understand that from the 0 minus sign. And the same thing for our green color coding. We said x goes to 4 plus, meaning that from right, let's follow our green line about the orange line, and we go to positive infinity. Positive infinity. And you may understand this situation by like 1 over 0.1 will be equal to 10, 1 over 0.01 will be equal to 100. Then you can see that as you increase the value in your denominator, it will approach to more and more infinity. This is why it goes to positive infinity and the vice versa for that pink line. Everything clear, I hope, right? Anything I missed again? No, right?
I don't think so, no.
Okay. So, how does a limit exist? Limit of a function. We have a rule for this. So, if fx, meaning a function has a limit at x is equal to a, let's say, it has to compromise with two conditions. The first one is limit fx, x goes to a plus, meaning that from right side, and x goes from a minus, meaning that from left hand side. Let's say the one from the right hand side, our limit is L1, and one from the left hand side, meaning the pink one, is L2. For a limit to exist, L1 and L2 has to be the same points. They have to be equal to each other. If L1 and L2 are not equal, then limit does not exist. And the abbreviation is DNE, we said, it does not exist. So I will go from right and also from left. I will see if a limit exists. They have to be equal. Those two have to be equal. From right and left, they have to give exactly the same answer. Let's see. We have an example over here. As you can see, this is how can I say, partial function. So it is divided into sides. How we called it again? Do you remember that?
I think it was piecewise function.
Piecewise,
right?
Yes, piecewise functions. So we have two conditions in one function. They follow up each other. So it says find the limits of this piecewise function at x is equal to 2, 0, and minus 1. We have to know and get familiar with the concept of critical values. Critical values are the values that make our function undefined. So I made a list over here for you. The first one is if it is 1 over gx, roots of gx makes our function undefined. Similarly, if we have a square root, gx having a value smaller than 0, log gx, if it is equal to or below 0, since a logarithmic function cannot take a negative value, and it will make it undefined. And if we have a sign diagram, the sign diagram values that we put here will also make it critical, which we will also discuss in the curve types, and it will be in the differentiation part, obviously. And lastly, if we have piecewise function just like this, the a values over here, the conditions, the domain that is given to us is critical because it makes it undefined. And as you can see in the orange box, this is the case here in our question, and it is the a is -1, -1, yeah, case for this question, as I said. So let's see now. For x is equal to 2, the first part, limit fx, x goes to 2. And this is not a critical value, so we can directly substitute it into the function. And 2 is obviously, let me make it look like this, 2. So in the piecewise function, this is the first one, 3x minus 2. Our domain fits into the first one in the piecewise function. Let's substitute it. 6 minus 2 is equal to 4. Limit at 4. a limit exists at 4. And the second one, x goes to 0, x approaches to 0. It is again the first one, and I can see that 3 times 0, 0, minus 2 will give us minus 2. So a limit exists as x approaches to 0, and the limit is at minus 2. However, we see that x approaches to minus 1 in the third part. However, x is equal to minus 1 is a critical value, as we mentioned in this orange box over here, since it makes it undefined. Hence, we have to use the condition that we have mentioned over here in the very first orange box. We have to check for two conditions. The first one is x a plus and x approaches to a minus, meaning that we will try to approach from both left side and also right side. Let's see how it worked. I once again used color coding. Green means minus 1 with a plus sign and minus 1 with a minus sign. Therefore, a limit exists just only if the result, the limit that we find in the green box and the pink box are equal. We substituted minus 1 into approaching from the right hand side. And from the question I can see that approaching from right hand side means that we will approach from the first side, because our domain says that x greater than negative 1. If x is greater than negative 1, I was already trying to approach from the right hand side, and our domain shows that the first domain shows that we are approaching from the right hand side. Hence, I can directly say that I will use 3x minus 2, I will substitute x with minus 1, and 3 times negative 1, negative 3, minus 2, minus 5. This is L1. I hope we understood. I try to approach from right hand side, hence I choose the domain in my piecewise function which approaches from the right hand side, the value that is greater than negative 1. And secondly, in the pink parts, I see that I'm approaching to negative 1 from the negative side with a minus sign. Hence, I check my piecewise function. I'm looking for the domain that is approaching from the more negative side of negative 1, and it is the second one over here, x squared plus 3 over x minus 2. Approaches from negative side. Hence, let's substitute our x, negative 1 value, the critical value, into the x value over here, our fx. Minus 1 squared, 1, plus 3, 4, over minus 1, minus 2, minus 3. Hence, our L2, second limit that we received from approaching from left side, is 4 over minus 2. But we realize that our L1 was minus 5, and L2 over here is minus 4 over 3. No, it does not have a limit, since L1 is not equal to L2 in the IBDP. It should be less, sorry. So in the IB exam, you have to write a statement just like this. Minus 5 is not equal to minus 4 over 3, so L1 is not equal to L2. Therefore, we will say that limit does not exist at x is equal to minus 1. I hope this is clear.
Burak, I want to add something.
Yeah, sure.
Guys, this is really important in the case of continuity and differentiability. So this part, the part that Burak is talking about is quite important. So if you have any questions, please ask, because the next part I will be explaining is going to be just about this, the application of limit. So if you have any questions, please write them and we can answer directly.
Definitely. So, shall I continue again? I hope everything is clear here. Check for the critical value and so on and so on. Okay, so converges or diverges. This is an important concept once again. So if limits as n approaches to infinity at series an is equal to L, where L is a real number, the consequence converges. Otherwise, meaning if L is equal to plus or minus infinity, it diverges. What does that mean? Let's understand it. If our limit approaches to a certain point, like 4, like 95, like 0, like 1, it means it converges because it gets closer, 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 and it is going to a certain point. A certain point. However, if our limit goes to infinity, plus or minus infinity, it diverges. It diverges. So if L is a real number, the consequence converges, and if L is equal to plus or minus infinity, it diverges for sure. So let's see some examples in this pink box over here. Okay, converges. The first one for the converging one. We are given a series 1/2, 1/4, 1/8, 1/16, 1/32, and goes on like this. So I realize that there's a sequence over here. An, meaning that my series has a rule 1 over 2 to the power n. Let's identify that because we will assume it just as if our fx. So limit n approaches to infinity, and I found my an to be this. Let's substitute infinity into n. 1 over 2 to the power infinity. We are dividing 1 by an infinity that is in the power. This is even more than infinity. So if we divide 1 with such a number, what result will we get? 0. It converges to 0 because 0 is a real number. It's not plus or minus infinity. Our limit is going to a certain point, so it converges. Second one, 1.72, 1.722, 1.72222. This is a recurring number. How do we solve recurring numbers? So x is equal to this, obviously. 1.7222222. It recurs at 2. So let's multiply this x by 10. 10x will be equal to 17.22222. Then let's multiply it by 100. 172.22222. Why did I do this? Because I realized that if I do this, let me choose a better color, like this maybe. Those parts in the 10x and 100x are equal. So if I subtract 10x from 100x, I will have 90x, and those parts will already cancel each other out, and 90x will be equal to 155. Nice, because x will be then equal to 155 over 90. I divided both sides by 90. And the result is 31 over 18, meaning that it approaches to the limit converges to 31.18. It is a certain point, therefore it converges. However, on the other side, we have divergence as well. It is given that an is equal to n to the power 4 over root n cubed plus n square. In this case, we can find diverging functions and series very easily. If the power of the numerator is greater than the power of the denominator, it diverges. Why? Because if the power of the numerator is larger, greater than the denominator, this means that when we substitute infinity in place of n, our function gets bigger and bigger and bigger vigorously, meaning that we are approaching directly to infinity, directly into infinity, because our numerator is getting bigger, 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 bigger. However, our denominator cannot catch it. If it is, for example, numerator is n to the power 4, it is growing with the power of 4, but we can see that in the denominator the greatest power is n cubed, and it is squared, so it cannot catch it, so it goes directly to infinity. Second example is 1, negative 1, 1, negative 1, 1, negative 1. Let's identify the sequence. An is equal to negative 1 to the power n minus 1. Okay, I found my series. Let's write it in limits notation. This is the notation. Now, when I substitute infinity into my n, I realize that I have something indefinite. Why? Because I see that if my infinity value is an even number, my series will give a -1 result. But if my infinity was odd number, my result would be 1. This means indefinite. And infinity is an indefinite value as well. So that's why we said if L is equal to infinity, it diverges. So indefinite, hence this series, it also diverges. Third example, the last example, for you to better understand the concept of diverging with a graph. I have fx is equal to 1 over x squared. This is the graph, again color coding. Let's approach from left side. At 0 we do not have any value because this is a vertical asymptote. Y is equal to 0 is, x is equal to 0 is a vertical asymptote. I approach from left. It will never become 0. It will be it will go on forever, and it will approach the infinity because it is not impossible to reach the value of x is equal to 0. And you can even see that, let me write it in this way, limits x goes to infinity for fx will give me a result like 1 over, normally we do not show it like this, but for you to better understand, I will just write it in this way, infinity square. I am dividing the number 1 with an infinite value, which will make it equal to what? Normally it will go to 0, but it goes to infinity. It does not converge to a certain point. That's why. It goes to infinity, and this is indefinite. So I have a question over here for you to also remember the very first chapter series. Determine whether sigma n is equal to 0 and goes to infinity for this notation converges or not. Okay. We have the denominator 7 to the power n. So we have plus over here. I said, okay, let's divide them. 4 over n over 7 to the power n, which is 4 over 7 to the power n, plus sigma. We can divide sigma in this way. If we are able to divide this function into two parts by using the common denominator, we can divide also the sigma with the same notation. And the second part will be 3 over 7 to the power n. Nice. So I realized something here. This means that this is a series. This is a geometric sequence, and it starts from n and goes to infinity. Let's use our data booklet. From the data booklet, we know that the sum of a geometric sequence at infinity is equal to S infinity. We have it directly in this way in the first part of the data booklet. U1, meaning the first term, over 1 minus r, where the geometric ratio coefficient is r, 1 minus r, for r being in an absolute value and smaller than 1, then we know that this is the formula. Okay, let's solve the first red part and the second red part. I realize that my first term is 1. Why? N is equal to 0. Our sigma notation says that the first term will start at n is equal to 0. I substitute 0. Something to the power 0 means 1. And r, meaning that our geometric sequence, how can I say, ratio, coefficient or something like that, 4 over 7. Why? 4 over 7. This is a geometric sequence. And the second one, same thing, n is equal to 0, 1, and r is 3 over 7, since this is a geometric sequence. Therefore, let's apply this formula. S infinity is equal to u1 over 1 minus r, and I will see that 1 over 1 minus 4 to the power 4 over 7, I'm just applying the formula, 1 over 1 minus 3 over 7. I see that it converges to 49 over 12. it goes to a certain point, 49 point over 12. Anything missing? I think it was a good example, right, again?
Yes, and it could be a question where we can see this in IB.
Because this is a combination of two chapters, two concepts.
And also, although you cannot see such questions in paper 1 and paper 2, it was asked in paper 3,
yes,
previous syllabus. Now we have a new syllabus and they could ask these questions in the new syllabus. Definitely. So let's be careful about it.
Definitely. So, I guess this was my last concept. Limits at infinity. What does it mean? So we are looking for limits at a point where x is approaching to infinity. We have three cases for limits at infinity. Let's imagine we have a function f(x) and it is represented in this form: ax to the power n, bx to the power n minus n plus da 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 da, then over this notation. Okay, this is our function. The part that we care about the most is the part in the numerator and denominator where we say we have the greatest exponents in the numerator and denominator. Let's see. This is under our scope. Case 1. If n is greater than m, meaning that the one term in the denominator with the highest power is greater than that one in the denominator, we see that our fx will approach to either positive infinity or negative infinity. Why? Because I explained it previously. We know that as it goes to infinity, the numerator gets bigger and bigger and bigger, much more faster than our denominator. That's why it goes to infinity. The second case, n and m are equal. The highest terms have the same exponent. Then our fx will be equal to a over d. Why? Because we know that both numerator and denominator are getting bigger and bigger and bigger in the same amount. They are getting bigger and bigger in the same amount. However, this means that at infinity, only a and d will matter. Which one will become bigger, which one will be smaller. That's why we say if nm is equal to m, our limit is at a over d. Case 3. m is greater than m. And this means that denominator gets greater and greater than numerator. This means that we are approaching to 0 because our denominator gets much bigger, much bigger, much bigger than our numerator, meaning that we are dividing our number, our results in the numerator with a much bigger result, meaning that we will approach to 0. This is just like the case of 1 over infinity. We are dividing a smaller number with a much greater number, therefore we are approaching 0. Limit will be at 0. Okay, so another concept. We have the horizontal asymptote when limits of x is approaching to positive or negative infinity for a function. Let's solve an example and understand it. So, by the way, for the first case, this doesn't work because, again, you remember, right? We have conventional asymptotes.
Yes.
Conventional.
Guys, there is an oblique asymptote, and we are going to talk about this later in other topics. But let's say they approach the infinity, but they have an oblique asymptote. We will talk about that more.
Yeah. So, an example. Find the horizontal asymptote of this function, 3x plus 4 over 5x minus 1. I can see that the term with the highest exponent here is 3x, and in the denominator it's 5x. So let's say this is n, x to the power 1, n is equal to 1, and x to the power again 1, so our m is 1, meaning that n and m are equal. So This means that at infinity, we will only look at the highest terms, 3x over 5x. And this will be equal to, since when I substitute infinity into x here, they will grow in the same amount. Therefore, we will just not see those x, and it will be equal to 3 over 5, which was actually a over d from the previous rule that we have just shown you. If you understand the logic, it will be much easier. You do not really have to memorize them, right? Again, you don't really have to memorize.
No, guys, you don't have to memorize.
Just understand the logic. Just understand the logic. If numerator gets much and much bigger because of having a higher exponent term, it goes to infinity. If they are equal, this means that they are growing in the same amount, so their coefficients with the highest terms will be important. And if denominator gets much and much bigger compared to numerator, it goes to 0 because we are dividing it with a larger number. So y is equal to 3 over 5. It converges to 3 over 5. Now, this is my last part. This is an excellent question, and this is definitely an IB question. Now, at this point, this is the reason why I say do not memorize. Try to understand the logic, because in IB, even L'Hopital may not help you to solve limit questions, or remembering or memorizing some formulas may not help you. Because we have a question like this. Find the horizontal asymptote of sine x over x cubed plus 1. You have to make your comments on that, because let's write it. Limit x approaches to infinity, sine x over x cubed plus 1. Now, actually, we didn't teach you L'Hopital yet, but you cannot use L'Hopital. It will give the same results. And I'm looking at it. What is the highest term in the numerator and denominator? Well, I do not really have them in the same form, one of them being in polynomial form, other than being in a trigonometrical form. But I know something. X is approaching to infinity, meaning that I know already the sine curve. This is the sine curve, right? Sine x. This one being 1 and this one being -1, right? So I see that if my x is approaching to infinity, nothing much changes about how it oscillates between 1 and -1. It always oscillates between them. Not a different answer. However, in the denominator, I see that when I substitute infinity into x for my denominator, meaning for x cubed plus 1, I realize that infinity cubed plus 1, we don't really make this notation, but just to make you understand, it is going directly into a greater infinity. So, I am dividing a value between -1 and 1, a small value, by positive infinity, x cubed plus 1. So, I can understand that I am dividing a value between 1 and -1 with an infinite value. Hence, it will approach to 0. Therefore, it will approach to 0. Because 1 and -1 is a small number compared to infinity cube plus 1, a much greater result. So I can see that y is equal to, y is equal to 0 is a horizontal asymptote, and you can either use your graphing display calculators or you can use your Desmos accounts to see that this is really the case. The horizontal asymptote is y is equal to 0. Therefore, this was end of my part, and I will just switch to first principles. But again, do you think we should switch our Zoom account first?
Yes, we don't have much time for Zoom. There's a 40-minute limit, so we will be back in a minute.
We'll be back in a second, yeah.
Yeah, we will be back in a minute with an important concept.
Yeah. Okay, so we are back.
Alright, guys. Let's start with first principles. Okay, let's wait for others because I think they were gone. Okay, guys, first principles is the basis of derivation, which is also the basis of integrals and also ordinary differential equations. So it's an important concept, and let's try to understand the logic behind differentiation before we teach you the differentiation. Okay, so let's start. Let me open my notes. All right. So our definition says that if the limit exists, then f prime a is equal to limit where h is approaching 0, and it is equal to this. And it is given in the formula booklet, so you don't have to memorize it. But I mean, we have to know the logic behind this concept. So I will teach you the concept. Okay, so as you know, the derivation is all about the gradient function. If you find the derivation of a function and you find the gradient function of it, where you can put any x value into the equation and then find a point at that specific point. So the logic behind it is, we know that gradient slope, you can see, okay, you can see it, is equal to y minus 2, y minus 1 over x2 minus x1. So we know that we have a function. It is equal to x, f function x. And let's say we have a step size, okay? And its step size is h. And it's a very small value. You do it step by step. Let's assume it's a very small value. If we move from x to xh, then it is going to increase by h, right? And if we talk about the y value, then the y value will change by fx plus h minus fx. So it is the same equation here, actually, the slope equation. I think it's coming a bit delayed, so don't worry. Let's not worry about it. Yes, and this is the logic. In order to teach this concept more clearer, let's solve one question, and I think you will understand this logic. Okay, so
actually, I have a question. So we are assuming that this h is very small, right? It is just like delta, because our followers may right now say that, wow, there is a difference here, so the curve is not actually as same as this purple line. But we are assuming that this h is very, very small.
Yes.
Yeah, right?
I mean, if you make h very big, like 1 or 2, if you move by 1 or 2, then you won't be able to find the gradient at that point. Because, for example, we have a curve, okay? And if we draw a tangent line over x, and if we draw a tangent line over over 2 or 3 steps ahead, then its gradient will change by a lot. So this is the logic. It has to be very small in order to find the gradient at that point. Okay, let's solve example. Right. Could you move down a little bit?
Yeah, sure. Is it okay?
Okay, let's solve this. Yes, it's great. Let's solve this question. I will choose green color. Yes, I think this is... Okay, let's solve. It says find dy dx from the first principles, and our equation is given here. Okay, let's solve it. Let's apply the first principles formula. Okay, so we know that it is a, x plus h. So we have to put x plus h into the place of x. Let's put it, and we put it here, 4 minus x plus h here, and then minus we have fx, and we just put x here, and it doesn't change actually, minus 4 plus x, and be careful about the signs here. I forgot to put it, I forgot to mark it, but it was like this, 4 minus x. Wait a second. My OneNote is lagging. Okay, let's not worry about it. It's lagging. Okay, so when we move down here, I'm distributing these. Let me put it here so our viewers are not confused. So, and then we remove these because they cancel each other. And when we do it, we find that minus h over h, and it is equal to -1. And when we actually, if we know the rules of differentiation, then we can see that it is actually -1. So you can verify your answer by using your derivation knowledge. Okay, let's solve the second example. It's a bit long, and don't worry about it. Just try to be precise with your algebra knowledge. Just be careful about it, and there's nothing to worry about. Okay, so I will open and close my OneNote. Okay, I'm back. Oh, so find dy dx for using first principles. Okay, so let's deal with x plus h. I'm writing it here. And let's put x plus h here, okay? And also x plus h here. I think you can see it, yes. And let's move here and just put what we wrote there. Actually, this was x here, and when we put x plus h, it's squared plus xh minus 1. Also, minus, we have a minus here. Be careful about minus, because when I used to work with first principles, I used to make that mistake a lot. It is minus 2x squared. We just put x here, and you can see the formula up there. And minus x and plus 1. Let's open them, okay? So let's expand them. When we expand it, we find 2x squared plus 4xh and plus 2h squared. And we can see that they actually cancel each other out. And when they cancel each other, we have this 2h squared plus 4xh and plus h over h. And when you see it, you have to eliminate the h here, because when you think about it, if you put h here, as Burak said, it's going to be undefined. So we have to get rid of that h here. This is the important part. And actually, we can get rid of it by taking the common factor of this equation in the numerator. And when we do it, we are left with 2h plus 4x plus 1. And we know that h is approaching 0. So this will be 0. And x is not approaching something, so we know that it is 4x plus 1 at the end. And when you check it, it's actually correct by using the rules of differentiation. I know that most of our viewers know this rule, but know the rules of differentiation, but we are taking it from the
zero level to hero
level. Yes, exactly. Okay, I think we are done with this concept, right?
Yeah, you can verify your answer. Anything that I have to add? No. I think this is very important to understand the concept of differentiation, right?
Exactly.
Yeah.
And if you have any questions, guys, please ask them.
And again, I would like to repeat, I also wrote in chat, you can go to our website, grab your FastFSNA card directly, quickly, for free, and reach all the notes that we are sharing together with Ege. We are trying to share as much as possible, as fast as possible, right, Ege?
Yes.
It is very easy. It will just take 2 seconds, and we have something like a Dropbox for FastFSNA card users, not only IB, but we are also sharing popular science, mathematics, philosophy, and so on. Special contents for you. So, the next concept again.
All right. It is continuity and differentiability. Actually, these names are very hard to write. I mean, I had to double check it from the internet. Continuity. I made a mistake while writing it. So let's talk about what Burak said in our live video, and this was actually important. I said it in the beginning, and This is going to be important here. Okay, that's right. So the rule says if f is, and this is actually function f is differentiable at x is equal to a, and f is also continuous at x is equal to a. But if it is not continuous, then it's not going to be differentiable. This is a very important concept to remember. This is also a topic from YKS, Turkish curriculum. So if you listen to this very carefully, then you will have no problem with IET math. This is Turkish curriculum lesson. Okay, so I wrote that here. If a function is continuous at x is equal to a, it doesn't have to be differentiable. But if something is differentiable, it has to be continuous. If it is continuous, it doesn't have to be differentiable. This is the rule. Okay, let's solve one very simple question. But could you move down a little, please?
Yeah, sure.
All right. Our example is actually the function of x is equal to x in absolute value. Like this, I will write green color. Exactly. So let's take a look at it. First, let's test for continuity. Okay. What was continuity? If the one x is approaching from left and x is approaching from right at a fixed value, have to be equal to each other. Okay, let's solve. We know that this is the sign for x is approaching to from right, and we know that this is x approaching from left. Let's solve them. Let's take their limit, and when we take the limit when x is approaching from left to 0, we know that it is 0. But if x is approaching to 0 from right, it is also 0. If they are equal, so we know that they are continuous. So there you go. We got the first condition. It is correct. Secondly, let's test for differentiability. Okay, let's take the differentiation of x. We are going to teach you the differentiation concept in the next video, but let's assume that you know this topic. If you don't, you can pass the rules of differentiation video that we are going to do very soon, and then come back for this topic.
And
but
also again, they may also think that you gave an actually pretty easy example, right? So they know that I guess differentiation of a function is equal to its slope at a point, and
yes.
This is in the form of y is equal to mx plus c, and we don't have c, and m is equal to slope. So you said x and negative x, so it's already 1 and negative 1, right?
Yes.
So they may also think about that way.
It is actually giving the slope function. So when you think about its graph, which is this, let's draw that. Yes, it is being seen. This is the x component, y component, and you can see that it is 1 and minus 1. No problem. Okay, let's take their derivative, and when we take the derivative, one is minus 1, and the other one is 1. They are not equal, but they have to be equal to be differentiable at a point. So we know that they are not equal, so they are not differentiable at x is equal to 0. So this was a very simple example, but let's pass to the next example, and this is going to be very, very important.
Sorry. Yeah.
All right. Our next example is very important, and it could come up in IB, in paper 3, in paper 1 or paper 2. It used to come up in paper 3 in the previous syllabus. Okay, so let's solve it. We have a piecewise function, and the function is given up there. And let's first test for continuity. Okay, so we have a critical value, as Burak said, and these critical values are very important for us, very critical for us. Okay, okay, x is approaching to 1 from right, and x is approaching to left from left to 1. This is important. Okay, so let's take the case when x is approaching 1 from right. And when we put 1 in place of x, let's put them, you find that it is 10. And the second one is when x is approaching to 1 from left, then we know that it is 13. What is it, guys? It's not continuous, right? If it is not continuous, can we say it is differentiable? Okay, let's see if we can say that. Let's come down and test for differentiability. And this is the tricky part, very important part. Okay, so let's take the differentiation of this. Okay, its differentiation is 3. And it's the differentiation for the case when x is approaching 1 from left. It is actually minus 2x plus 5. And we have to insert 1 in the place of x, because we are trying to know that we are trying to find out if it is differentiable at x is equal to 1. Okay, when we put it, we know that it is 3, but they are equal. So is it differentiable? Guys, what are your answers? I would like to know your answers in the comments section. I know that our viewers are silent, but we have to be interactive in order to learn. Okay, so what is the answer, guys? Is it differentiable or not differentiable? Actually, you can see the answer, but
Okay, let me answer. It's not.
It's not. Yes, thank you, Burak. Thank you.
You are welcome.
Okay, the answer is it's not differentiable at x1 because it is not continuous. First it has to be continuous and then differentiable. It cannot be like not continuous and differentiable. Doesn't work. It has to have continuity first. Yes. So I think that's it.
So this was the end of our live video, right, again?
Yes. It was a quick one.
It was a quick one.
I think very, very efficient one.
Yeah. So it took 50 minutes almost, and I can now see that we have learned limits, continuity and differentiability, and also first principle of differentiation. So please follow up, stay tuned, and you may also visit our website, apply for being part of Felsefesi'nde team, because we are starting new projects, right, Ege? You know them already?
Yes.
Big projects. And you can also join us as an IB student to contribute to the development of IB student profile. And we wish you the best. So calculus episode 2, 3 will also come up. And what we suggest is that maybe you can right now solve past paper questions to enhance your understanding. And this was all for us. And please do not forget to grab your Felsefesi'nde card for free. And we would be very glad because we are making a lot of effort with Ege, and I really appreciate Ege, also your effort
and
for
also
not taking.
I appreciate Burak for
thank
his
you very much, bro.
initiation to start this project.
Thank you very much, bro. I mean, and if you also, as our followers, join our Felsefesi'nde team or grab your Felsefesi'nde card, reach our notes, class notes, we are sharing all of them, and we are also uploading our past papers that we have solved, just like those things with color codes. I hope that they will help you. So we wish you all the best, and
we will be back with differentiation in the next video.
Yeah.
So stay tuned, please.
And if you have any requests, just like a topic, a class, another thing, you can just directly reach to us from our website, Instagram, Twitter, wherever you want. And thank you very much for being together with us. I hope you enjoyed it. See you. Bye-bye.
Bye.
Bitti kanka.